So let's take a look at the last problem from the last page of lecture 1.3 in my slides. So the intention of this slide was to give you guys some practice looking at not only developing linear models, but using MATLAB as well, or Excel, to plot these. So I'm going to go through a couple different solutions to this to show you some ways that we could go through and get what they're actually asking us to find, which is the functional relation between f and x. So let's take a little bit closer look at this problem statement here. So they tell us that the distance a spring stretches from its free length is a function of how much tension is applied to it. They give us a table with a spring length in y that was produced in a particular spring by the given applied force F. So here's the applied force F, here's the spring length y there. So they tell us that the spring's free length is given to us by 4.7 inches. So now what they want us to find is a functional relation between F and X, our force, and our spring length. The extension of the free length they give us by this relationship here, that X is equal to Y minus 4.7. So we can take this here to minus 4.7 from each one of these here in order to get the free length of the spring. So what we can do from here is several different options. We could solve it by hand. We could use Excel, we could use MATLAB, we could use Python. There's all types of options. I'm going to go through kind of the author's solution to this here, where they just solve it by hand, look at the problem statement, realize we're dealing with a spring, different lengths, stretch versus unstretch, find F equals Kx, and go from there. I'll go through how to do it in Excel and plot it and back out a trend line, and I'll go through MATLAB of how to plot it and back out a trend line as well. So if we look down here at the solution from the author here, just a hand solution, they tell us that the physical considerations require the model to pass through the origin so that we seek a model in the form of F equals Kx, typical equation for spring, where K is our spring constant. A plot of the data, so we can still plot it whether we do it by hand or one of the numerical methods, shows that a good line drawn by eye, if we do it by hand, is roughly F is equal to 0.2x, where 0.2 would be the slope using a linear approximation, y equals mx plus b, where b is the intersect at the origin. So from that, we can estimate k to be, from this here, 0.2 pounds per inch. So now I can take the information from the table they give us in the problem statement and plug it into Excel. Do that over here. They have my spring length that's given to me, my force is given to me. I plug those values in exactly as they are from the table, and then I use the relationship that they give us in the problem statement there, where we want to subtract 4.7 from the spring length to get our unstretched spring length here. So we do that now. We end up with this relationship here. So I can simply use Excel to subtract 4.7 from each of these values there to create this new vector over here. So then what I want to do is plot both of these. I can go insert, I want to go to a scatter plot over here, and I can change the layout of this however we want to for labels on the axes. Come through here, and what I'm going to do now is I can click on the data points here. If I right click on this, I can go down to add a trend line. When I do a trend line here, I can select that I want to be linear. From that, I can also say that yes, we know this goes through the origin here at 0, 0, and I want to display my equation there. So right up here now, I get my equation where y equals mx plus b, where my plus b is 0 because it goes to the origin, or my f equals kx here, where this is my k value there. And there we can see there's our 0.2 value that we saw when we did our approximate solution when we solved it by hand. So if I go over here and I were to do out this chart a little bit more detail, what I can see in this here is I can change my axes and my labels, sizes of things, so it's a nice clear graph. And this is what I really want to add to a solution to a problem like this. So another option to solve this problem is by using MATLAB. So within MATLAB, what I've done is I've created a new script here. So within the script, I've titled it now Problem 1.15, Developing Linear Models. Now, at the top of this here, I like to clear all the variables that I may have had from any other previous work I've been doing in MATLAB. Once everything's cleared there, we've cleared out our command window and all our variables, we can then put in the information for the two vectors they give us in the problem statement. So they tell us in that table we have a force vector and the spring length there. So I go through, put in my MATLAB code for the vector for the force. We can put commas in here if we want to help organize it, but we don't have to. It's not going to change anything there. And I haven't put a semicolon at the end of this because I want to be able to go down to my command window and make sure it is exactly what I want it to be for each of these vectors. If you want to save a little computing time and not clutter up your command window, feel free to add a semicolon to the end of these so you don't have to look at them. I also have information about the free length here. They tell us it was at 4.7, so I create a vector there. I call this u. And to find the change in the length here, I say s equals y minus u, the spring length minus the free length there, and that gives us this change in length vector here for the spring. And from this information that we have put in here, we can then find the slope of this line, assuming a linear approximation here, y equals mx plus b, so our slope is equal to f over s, which is our force over this length down here now that we've just solved for. Now from this here, the next thing I want to do is to be able to plot this out. When I plot this out here, I use this plot command function, the two variables, my s and my f are the two variables moving here, and I can label both the axes right here. So the next thing, once I have all this information done, I go ahead and hit run. When I run this here, it pops up my graph, and as we can see from what we put in down here, it's labeled these length and force over here. So then we can go through and look at this here, and we could, if we hadn't done this information right here to get the slope, we could go through this and back out a trend line from this as well. So if we want to get this trend line within MATLAB in the figure, easy way to do it is just go right into tools, go down to basic fitting here. It'll pop up some options for us over here. We can select our best fit. It's roughly linear here. We want it to be linear. It's pretty close to going right through our origin, which will be good enough for what we're doing for this problem here. So we can say linear, and then it pops out our line. Yeah, and this would be right through the origin. This would be 0, but still gives us our y equals mx plus b here, where our m is our slope, which is, again, roughly that 0.2 value.